In early 1916, Lieutenant Colonel Peter Norman Nissen walked through muddy building sites near Ypres. He wasn't thinking about making history. He was watching British soldiers die from cold weather whilst waiting for proper buildings. And that's when everything changed. The Western Front had destroyed normal building methods. Wood was running out fast. Skilled builders were fighting in trenches. Every building needed to survive bombing attacks. Nissen was a Canadian-born mining engineer working with the Royal Engineers. He'd spent months watching something strange. Piles of corrugated iron sheets lay abandoned near supply areas because nobody knew what to do with them. But here's what caught his attention. These curved metal panels were meant for roofs. They were stacking up whilst men froze in canvas tents that fell down under snow. The brilliance of Nissen's answer wasn't fancy. It was dead simple. He took those corrugated sheets and bent them into a half-circle shape. This created a building that needed no supports inside and could go straight on the ground. In March 1916, he built the first test model at Ypres. He used only standard tools and 6 soldiers who'd never built anything before. The building went up in under 4 hours. Think about that for a moment. When Nissen showed his design to British Army Command, he made one promise. Any infantryman with basic instructions could build it in 3 days, and all the materials could fit on one single lorry. The British Army tested it straight away at Richborough Port. The 172nd Tunnelling Company put up 20 huts in April 1916. Each hut was 16 feet wide and used about 600 square feet of corrugated steel. The curved shape meant rain and bomb pieces slid off instead of going through, and the lack of straight walls meant no weak spots where shells could catch and rip. By June 1916, Nissen Huts appeared across every British area of the Western Front. The War Office placed its first massive order in August, 10,000 units to be made and shipped before winter arrived. What made the Nissen Hut truly special wasn't just speed. It was removing skilled workers from the whole process. Normal military building needed carpenters, bricklayers, and engineers. Nissen's design needed none of that. The corrugated sheets came with holes already drilled exactly 14 inches apart. Wooden end walls arrived as ready-made panels. The foundation was optional. Crews could bolt the hut straight to wooden sleepers or even to pack dirt if needed. A sergeant and 5 privates could unload materials, lay out the base, and have the building weatherproof before nightfall. Now here's where it gets really interesting. During the Battle of the Somme in late 1916, building teams were putting up Nissen Huts within artillery range. This gave immediate shelter for wounded men coming from the front lines. The hut's size was worked out for maximum efficiency. The 16-foot width allowed 2 rows of beds with a center aisle. This housed 30 men comfortably, or 50 in emergency situations. The curved roof rose to about 15 feet at its peak. This gave enough height that men could stand upright in most of the inside. Fresh air came from panels at each end you could adjust. And the corrugated steel's natural air gaps stopped the condensation problems that ruined canvas tents. By the armistice in November 1918, British forces had put up over 100,000 Nissen Huts across Europe, the Middle East, and Africa. They worked as sleeping quarters, hospitals, supply stores, and command posts. Anywhere the army needed buildings fast. The design papers Nissen gave to the War Office in April 1916 showed why his hut beat every other choice. Normal military buildings relied on vertical framing, posts, beams, and supports that had to be cut, fitted, and joined perfectly. Nissen got rid of the entire idea of framing. His curved corrugated sheets held themselves up. This meant the walls and roof were the same thing. When you bolted one sheet to the next, you weren't just adding coverage. You were creating structural strength. Each 16-foot section overlapped the previous one by 3 inches. The bolts went through 3 layers of metal. This created a continuous shell that spread weight and pressure across the whole surface. The building steps were deliberately foolproof. Step 1. Lay wooden base plates in a rectangular outline. Step 2. Bolt vertical wooden ribs to those plates at 7-foot gaps. Step 3. Attach the first corrugated sheet to the ribs and bolt it to the base. Step 4. Add the next sheet, overlapping and bolting it to the first. Repeat until the half circle was done. Step 5. Put in the wooden end walls, which came with doors and window frames already fitted. Total building time with an experienced crew, 72 hours. With completely green troops, 4 to 5 days. The British Army tested this repeatedly at training camps in Dover and Southampton throughout summer 1916. They timed different groups to work out reliable building schedules. What separated the Nissen from later copies was its relationship with available materials. Nissen designed around what Britain could actually make during wartime. The corrugated steel sheets were 26 gauge, thick enough to resist damage, but thin enough that 3 men could carry a section without machines. The curve radius was worked out precisely. Standard sheet metal rollers at British factories could form the shape without retooling. Every bolt was 7/16" diameter, the same size used in shipbuilding. This meant supply chains didn't need special stock. The wooden parts, end walls, base plates, and inside ribs came from whatever timber was available. Nissen's specifications allowed for pine, oak, or even salvaged wood from damaged buildings. Field adjustment made the system nearly universal. In Mesopotamia during 1917, British forces built Nissen Huts without the wooden end walls. Instead, they used bricks scavenged from ruined villages. In Egypt, engineering units set the bases straight on sand. They used inside poles cut from local palm trees instead of milled timber. The core idea stayed the same. Those curved corrugated sheets would form a weatherproof shell no matter what you did with the rest. A Canadian unit at Vimy Ridge in March 1917 put up a Nissen Hut during active bombing. They worked in 30-minute shifts between artillery attacks. The building was working within 18 hours. It immediately housed 40 wounded men brought from the Ridge assault. The speed advantage became clearest in moving materials. A single railway flat car could carry enough materials for 8 complete Nissen Huts. That's 48 sheets of corrugated steel, wooden parts, and hardware. At the military camp in Étaples, France, building teams kept a record pace throughout 1917. 1 finished hut every 6 hours when working in rotation. By October 1917, Étaples had grown to house 100,000 troops. Almost all lived in Nissen buildings. The camp's hospital section alone had 300 huts. This gave bed space for 12,000 patients. When the German spring attack hit in March 1918, suddenly 20,000 more wounded needed shelter. Crews put up 70 new hospital huts in 11 days. Now, let's jump forward to America's involvement. The United States Navy sent its first engineering team to Britain in September 1940. That's 15 months before Pearl Harbor. Commander George F. Dora was stationed at the Bureau of Yards and Docks in Washington. He had clear orders: study British temporary building methods and work out if they could support American military expansion. Dora spent 6 weeks touring RAF bases, Army camps, and Royal Navy sites across England and Scotland. His classified report, filed in November 1940, gave 18 pages to the Nissen Hut. He wrote down building times, material details, and interviewed British building officers who'd used them since 1916. Dora's conclusion was direct. The Nissen Hut was the fastest field building ever designed, but American forces would need changes. The changes began immediately after Pearl Harbor on the 7th of December, 1941. The Navy Civil Engineering Corps chose Quonset Point Naval Air Station in Rhode Island as the development site. It had active building projects and direct rail access for shipping test models. Commander John Barney Cyrus led the design team. He worked with specifications Dorr had brought from Britain. He also had actual Nissen Hut blueprints the British government gave under Lend-Lease arrangements. The first American test model came out in February 1942. It looked similar to the Nissen, but carried basic differences that would affect every unit built after. American engineers changed the structural logic. Where Nissen used corrugated sheets as self-supporting pieces, bolted straight together, the Quonset design introduced an internal steel framework. This framework had curved steel arches, basically ribs made from formed steel channels. They stood independently and supported the corrugated panels. The panels no longer carried building loads. They were cladding attached to the frame with self-tapping screws rather than through bolts. Cyrus argued this approach would create stronger buildings. They could support heavier equipment loads and give better anchor points for electrical and plumbing systems. He was correct on both counts, but he'd introduced a complication the Nissen deliberately avoided. The framework requirement meant Quonset Huts arrived at building sites as more components needing more building steps. A standard 40-foot Quonset needed 14 steel arch ribs. Each weighed about 90 pounds. They had to be positioned at specific gaps and bolted to foundation plates. Only after the frame was complete could crews attach the corrugated panels. Nissen assemblies started with the panels themselves and built outward. This philosophical difference, framework first versus panels first, added between 12 and 18 hours to building time. Tests at Quonset Point in March 1942 proved this. Navy officials accepted the trade-off because they prioritized building permanence over deployment speed. American planning assumed most bases would be occupied for years, not weeks. The Quonset also had features the Nissen design didn't have. Interior insulation became standard. Blankets of fiberglass sandwiched between the steel panels and interior plywood lining. Electrical wiring was built into the framework during assembly rather than surface-mounted afterwards. Wooden floors replaced the Nissen's packed earth or wooden duckboards. Windows were larger and included screens. Doors used American standard hardware instead of British hinges and latches. Each improvement made sense from a comfort and function standpoint, and each added weight, parts, and building time. A complete Quonset Hut package weighed about 30% more than equivalent Nissen materials. This needed more lorries or rail cars for transport. By May 1942, the Navy had standardized 3 Quonset sizes: 20 feet wide, 40 feet wide, and the largest at 50 feet wide. Production contracts went to the George A. Fuller Company and the Strand Steel Corporation. Both had experience with pre-made steel building. The first mass-produced units shipped to naval stations in June 1942. The steel framework that defined the Quonset created a parts dependency the Nissen never had. Each arch rib arrived as a pre-formed piece of steel channel bent to the exact radius needed for that particular hut size. If one rib was damaged during shipping, bent, cracked, or missing bolt holes, the entire frame's shape could fail. Nissen Huts tolerated imperfection because the corrugated panels flexed and adjusted as crews bolted them together. The panels themselves corrected minor alignment errors. Quonset ribs had to align perfectly before any exterior panels went on. This meant building crews spent hours using levels, plumb lines, and measuring tapes. They had to ensure every rib stood at exactly 90 degrees to the foundation and matched the spacing templates. The bolt count told the story of increasing difficulty. A 16-foot Nissen Hut used about 200 bolts total, mostly connecting corrugated panels to each other and to the wooden base. A 40-foot Quonset Hut needed over 700 bolts and screws. 14 arch ribs bolted to foundation plates used 6 bolts each, totaling 84. Cross-bracing between ribs added another 100 bolts. Attaching corrugated panels to the framework with self-tapping screws meant 16 screws per panel. A 40-foot Quonset used roughly 30 panels. Then came the inside work, plywood lining attached to the ribs, insulation fasteners, electrical box mounts, and floor joists bolted to the foundation. Every extra fastener was another chance for building delays when tools broke or hardware went missing in the field. American production methods emphasized standardization that oddly reduced field flexibility. Quonset parts were made to tight tolerances in stateside factories. This ensured pieces fit together perfectly under controlled conditions, but combat zones weren't controlled conditions. When the 804th Engineer Aviation Battalion arrived at Henderson Field on Guadalcanal in January 1943, they discovered something. Humid conditions had caused some steel ribs to rust at bolt holes during the Pacific crossing. The ribs couldn't be changed or replaced with local materials. The entire building depended on those precisely formed arches. The engineers had to wait 3 weeks for replacement ribs to arrive from Pearl Harbor. Troops slept in tents whilst they waited. The insulation system, whilst giving superior comfort, became a building bottleneck. Quonset specifications required fiberglass batting to be fitted between the corrugated exterior and interior plywood lining. This meant crews had to work in 3 stages. Erect the frame, attach exterior panels, then go back inside to fit insulation and interior walls. Nissen Huts were single-stage buildings. Once the corrugated panels were up, the building was complete and livable. Inside improvements came later if time and materials allowed. At the Navy's Camp Endicott in Davisville, Rhode Island, where CB battalions trained in 1943, instructors timed both systems. An experienced crew could finish a Nissen-style hut in 48 hours. The same crew needed 96 hours for a comparable Quonset with full insulation and interior finishing. That's double the time. Electrical work added another layer of pre-planning that slowed field deployment. Quonset huts came with conduit pathways built into the framework. This meant electricians had to work at the same time as building crews, rather than after the building was complete. At naval air stations with abundant electrical contractors, this parallel building worked efficiently. But in forward combat zones with limited personnel, it created problems. Having electricians occupy the worksite while structural crews were still bolting ribs together created scheduling conflicts. The 6th Naval Construction Battalion in the Solomon Islands reported in April 1943 something important. Electrical requirements delayed average Quonset completion by 2 full days. This happened because qualified electricians were rotating between multiple building sites. The floor system represented perhaps the most significant speed penalty. Nissen huts had no built-in floors. Troops laid wooden duckboards or poured concrete after the building was up. Quonset specifications required pressure-treated floor joists, plywood subflooring, and finished wood flooring, all fitted during initial building. This kept the inside clean and comfortable, but it added an entire phase of carpentry work. When Major General George Patton's Western Task Force landed near Casablanca on the 8th of November 1942, his supply officers carried orders for immediate camp building. This was to support 35,000 troops. The invasion plan allowed space for Quonset huts shipped from Virginia, but combat conditions forced field commanders to make calculations the Navy hadn't tested at Quonset Point. Lieutenant Colonel Paul Thompson commanded the 16th Engineer Battalion. He watched his crews struggle with the steel framework in sand that wouldn't hold anchor bolts. The foundation plates designed for firm ground or concrete pads twisted when tightened. Moroccan coastal sand compressed unevenly. Thompson's after-action report, filed in December 1942, noted something crucial. His crews needed 4 days per Quonset hut. Most time loss came from stabilizing foundations and shimming framework ribs to make up for uneven settling. British forces in the same North African theater were simultaneously using Nissen huts they'd shipped from Alexandria. The 512th Specialist Team Royal Engineers set up a field hospital outside Algiers starting the 12th of November 1942. Working with local Algerian laborers who spoke minimal English, the team finished 16 Nissen Huts in 9 days. Their technique got rid of foundations entirely. They laid railway sleepers straight on graded sand. They bolted the corrugated panels to those sleepers. They stabilized everything with sand berms piled against the exterior base. When windstorms hit in late November, several Quonset Huts under building toppled. Their frameworks weren't yet covered with panels. The Nissen buildings, already complete with their self-supporting shells, stayed standing. The Pacific Theater showed even starker differences. On Guadalcanal, the 1st Marine Division began receiving Quonset Huts in February 1943. This was after months of fighting in muddy tent camps. Gunnery Sergeant Robert Leckie, whose memoir documented the campaign, described watching building crews work. They worked in 100-degree heat with 80% humidity. The steel framework parts were too hot to handle with bare hands by mid-morning. Crews worked shortened schedules, dawn until 10, then evening until dark. This stretched 5-day building estimates into 2-week realities. Meanwhile, Australian forces supporting operations from Port Moresby used Nissen pattern huts made in Sydney. Australian war production records show these simplified versions got rid of even the wooden end walls. They used corrugated steel throughout. Building teams reported average assembly times of 36 hours. Timing mattered most during rapid base expansion. When Admiral Chester Nimitz ordered the development of Funafuti Atoll in the Ellis Islands during March 1943, Navy planners needed something specific: housing for 5,000 personnel within 60 days. The 2nd Naval Construction Battalion arrived with both Quonset materials and some British Nissen Huts. These were acquired through Commonwealth supply channels. Battalion Commander Lieutenant Commander Joseph Blunden split his crews to test both systems. They tested under identical coral atoll conditions. His official report in May 1943 gave exact figures. Nissen Huts averaged 54 hours from first foundation timber to completed building. Quonset Huts averaged 91 hours. The gap came mainly from framework alignment and interior finishing requirements. The speed difference became critical during emergency expansions. After the Battle of Midway in June 1942, the Navy needed immediate hospital capacity at Pearl Harbor for incoming wounded. The existing hospital couldn't handle the surge, so building battalions put up temporary ward buildings next to the main facility. Using Quonset Huts with their required foundations, frameworks, and interior systems would have meant a 2-week building timeline. Instead, crews used a hybrid approach. Nissen-style corrugated shells put up in 3 days, with interior medical equipment fitted afterwards. Those emergency wards stayed in service through 1944. They housed over 2,000 patients during their working period. Weather resistance showed unexpected trade-offs. Quonset insulation kept insides comfortable in extreme heat and cold, but the complex wall assembly created moisture traps. In the Aleutian Islands during 1943, where fog and rain were constant, insulated Quonset Huts developed condensation. This formed between the exterior steel and interior plywood. It led to rust and mold. Nissen Huts, with their single-layer building and natural ventilation through corrugation gaps, stayed drier, despite being less comfortable. American industrial capacity transformed the Quonset into a mass production phenomenon the handcrafted Nissen could never match. By July 1943, the Strand Steel Corporation's factory in Richmond, Indiana, was producing 200 complete Quonset Hut packages daily. They shipped them to both coasts for Pacific and European deployment. The George A. Fuller Company's plant in Pennsylvania added another 150 units per day. This production volume, over 100,000 huts annually, required standardization so rigid that every part had to be interchangeable across all units. A steel rib made in January 1943 had to fit perfectly with panels and hardware made in August 1944. American factories achieved this precision through die forming and jig-based production. The British cottage industry approach to Nissen manufacturing never attempted this. The standardization philosophy extended beyond just physical sizes. Quonset huts came in exactly 3 widths, 20, 40, and 50 feet, with lengths in 10-foot increases. This modular approach meant logistics offices could calculate shipping requirements precisely. A standard 40-foot flat carried one complete 40 by 20 package. Transport ships allocated cargo space in Quonset unit increases. Supply depots stocked replacement parts, knowing that any 20-foot arch rib fit any 20-foot hut. This worked regardless of when or where either was made. The system got rid of the improvisation that made Nissen huts flexible, but also made them inconsistent. Cost accounting showed where American engineering priorities differed from British expediency. In 1943, a complete 40 by 20 Quonset hut cost the Navy about $850. This included all materials, hardware, insulation, electrical parts, and flooring. A comparable Nissen hut, based on British production records from 1918, cost about $230 in inflation-adjusted 1943 currency. The Quonset's superior comfort and electrical systems justified the higher price in American buying doctrine. But that 300% cost increase mattered significantly when multiplying across thousands of units. The total American spending on Quonset production exceeded $140 million by war's end. Production volume numbers told competing stories about success. The United States made about 170,000 Quonset huts between 1941 and 1946. That's an average of 34,000 per year. Britain produced roughly 100,000 Nissen huts just during World War I. Between 1916 and 1918, averaging 50,000 per year, with far less industrial infrastructure. The difference wasn't manufacturing capability. It was design complexity. Nissen huts needed corrugated steel sheets, basic fasteners, and rough timber. Any sheet metal facility could produce parts. Quonset huts needed specialized steel forming for the arch ribs. They needed precise die cutting for panel mounting holes, and coordination between insulation suppliers, electrical part makers, and lumber mills. The engineering trade-offs became clearest in adaptability. After initial building, Quonset huts could be upgraded. Crews could add partition walls, fit heating systems, run additional electrical circuits, and mount heavy equipment to the steel framework. These capabilities made them suitable for permanent installations, like stateside training bases and rear area headquarters. Naval Air Station Alameda in California received over 400 Quonset huts in 1943. They served as workshops, classrooms, and administrative offices. Many stayed in use until the base closed in 1997, some for over 50 years. That longevity proved the American approach valid for installations where permanence mattered more than building speed. But the framework that enabled those upgrades became a liability in temporary field use. When the 43rd Infantry Division moved from Guadalcanal to New Georgia in June 1943, they couldn't take apart and transport their Quonset huts. The steel ribs, once bolted together, were difficult to separate without damaging threads. The screwed-on panels could be removed, but without the framework, they were useless. The entire camp infrastructure, 42 Quonset huts, stayed behind, abandoned. Nissen huts took apart almost as quickly as they went up. The bolted panels separated cleanly and could be reused elsewhere. British forces routinely relocated Nissen camps, moving the same buildings from Egypt to Italy to Greece as front lines shifted. The real difference between Nissen and Quonset legacies appeared not during wartime, but in the decade after. When World War II ended in August 1945, the United States military found itself with something. About 70,000 surplus Quonset huts scattered across domestic bases that were rapidly closing. The War Assets Administration, tasked with selling military surplus, began selling complete Quonset huts to civilians in 1946. Prices ranged between $200 and $600, depending on size and condition. That same year, over 15,000 Quonsets were bought by farmers, small businesses, and housing desperate families across America. The huts' built-in floors, insulation, and electrical systems made them immediately livable as homes, workshops, or storage buildings. This civilian adoption created an American architectural phenomenon that lasted decades. Drive through rural Iowa, Kansas, or Nebraska today. You'll still see Quonset huts serving as machinery sheds and grain storage. Small airports across the Midwest used them as hangars through the 1970s. The University of Illinois housed returning veterans in a Quonset village from 1946 until 1972. 260 huts providing temporary family housing that became semi-permanent. Nothing replaced them. These buildings succeeded in civilian use precisely because of the features that slowed their battlefield deployment. The insulation kept them comfortable year-round. The strong framework supported shelving, equipment hoists, and modifications. The finished insides accepted drywall and paint for those wanting conventional appearances. Britain took the opposite approach with Nissen Huts after 1945. The military wanted them gone because they symbolized wartime austerity. Thousands were taken apart, with the corrugated panels sold as scrap metal during the post-war steel shortage. Some found civilian use. Farms in Yorkshire and Scotland converted them to sheep barns and equipment storage. But the British government actively discouraged civilian retention. They wanted to distance national identity from wartime temporary architecture. By 1955, most Nissen huts had vanished from Britain, except on remote military ranges and agricultural properties where practicality outweighed aesthetics. The few surviving examples today are either preserved as historical artifacts or hidden on private land. Owners value the weatherproof storage more than appearance. The architectural establishment treated both designs with disdain that revealed class prejudices about temporary building. American architectural journals in the 1950s rarely mentioned Quonset huts, except to condemn them as visual blight. Frank Lloyd Wright reportedly called them metal pig shelters, unfit for human habitation. British architects were even harsher about Nissen huts. One 1948 Royal Institute of British Architects publication described them as corrugated embarrassments. They should be eliminated from the landscape as quickly as economically feasible. This professional hostility ignored the practical reality. Both designs had sheltered millions of people effectively and economically when alternatives didn't exist. Commonwealth nations developed their own variants that often returned to Nissen principles. Australia's post-war reconstruction included simplified curved roof huts that got rid of American framework complexity. These buildings were used for immigrant housing and remote infrastructure through the 1960s. They prioritized speed and cost over comfort features. Canada's Department of National Defence continued making Nissen pattern huts for northern bases. Extreme cold made insulated Quonsets impractical there. The single-layer metal building prevented the catastrophic ice damming that plagued Quonset roofs when snow loads exceeded design limits. The military eventually moved beyond both designs. By the Vietnam War era, the United States had developed modular containerized housing. This could be transported by helicopter and assembled even faster than Nissen huts. These systems used aluminum frameworks and fabric panels, weighing a fraction of steel building. Modern military operations use expandable container shelters that deploy in hours, but these high-tech solutions cost exponentially more. A current military shelter system runs $50,000 compared to the $850 a Quonset cost in 1943. When adjusted for inflation, modern systems cost roughly 6 times more per square foot than their World War II predecessors, whilst providing similar function. The fundamental lesson embedded in the Nissen versus Quonset story is this: military logistics doesn't always benefit from engineering improvement. Peter Nissen created his hut by asking one question: what's the absolute minimum needed to keep soldiers dry and alive? His answer: curved corrugated metal bolted together. This ignored every conventional building principle. No foundations, no framing, no skilled labor required. Just metal sheets and bolts. That ruthless simplicity meant a sergeant and 5 exhausted infantrymen could build shelter in 72 hours, even whilst under artillery fire. The American engineers who designed the Quonset asked a different question: how can we make this more comfortable and permanent? Their answer was objectively better architecture, but practically worse emergency shelter. This tension between optimal and adequate appears throughout military history. The M1 Garand rifle was superior to the bolt-action Springfield in every measurable way, but it was also heavier, more complex, and needed more maintenance. Sherman tanks were mechanically reliable but under-armored compared to German Panthers. American forces won with adequate equipment deployed in overwhelming numbers, rather than perfect equipment deployed slowly. The Quonset followed this pattern. It was better shelter than the Nissen, but armies needed shelter faster than they needed it better. When the 1st Marine Division was fighting in Guadalcanal mud during late 1942, something mattered more. Having a weatherproof building in 3 days would have mattered more than having an insulated, electrified building in 10 days. Modern military doctrine has largely forgotten the speed versus quality calculation that World War II forced constantly. Current U.S. military building standards assume infrastructure will be in place before major troop deployments, that supply lines will be secure, and that building can happen without enemy interference. These assumptions held true in Iraq and Afghanistan. American forces controlled airspace and had months to build forward operating bases. But they wouldn't hold in peer conflict scenarios, where contested logistics and rapid position changes mirror World War II conditions more than recent counterinsurgency operations. The Marine Corps recognized this gap in 2019. They reintroduced expeditionary advanced base operations, essentially relearning the lesson that speed of deployment matters more than comfort of facilities. The engineering philosophy difference extends beyond just military applications. Modern building everywhere prioritizes complexity over simplicity. Building codes require electrical systems, insulation standards, foundation specifications, and dozens of other features. These make buildings better but slower and more expensive to build. This makes perfect sense for permanent buildings, but it creates problems for emergency response. After Hurricane Katrina in 2005, FEMA needed immediate shelter for thousands of displaced families. The temporary housing they provided, small manufactured homes, required concrete foundations and utility hookups. They took weeks to fit per unit. Nissen-style buildings could have been put up in days using only the devastated area's existing infrastructure. This would have given immediate shelter whilst permanent reconstruction proceeded. The 170,000 Quonset Huts America produced represented genuine industrial achievement. They provided shelter for millions of personnel across every theater. They served well in their intended role as semi-permanent base infrastructure. But they couldn't match what 6 British soldiers accomplished in 1916. Building weatherproof shelter in 3 days with nothing but hand tools and determination. That capability, that speed, that brutal simplicity was the actual innovation. The Quonset improved everything about the Nissen except the one thing that mattered most in combat: getting soldiers out of the mud and into shelter before the next bombardment started. The corrugated curved huts still standing across farmland and former military sites are monuments to different philosophies. The surviving Quonsets prove American engineering made them durable enough to outlast their intended purpose. The vanished Nissen Huts proved British engineering made them simple enough that armies could build them anywhere, any time, under any conditions, and then abandoned them without regret when the front lines moved forward. Both approaches worked, but only one could be built whilst the shells were still falling. And that's the difference between architectural success and battlefield necessity.